Hey there, it's Shannon Magic-Myers, and today we will be checking out section 2.5 of the ZIL Differential Equations intro book, and this section is called Solutions by Substitution. All right, so here we go. When a differential equation doesn't match up with one of the classes of equations that we know how to solve, we can try one of the following substitution procedures. So we basically are going to try to, make this look like a linear equation where we find an integrating variable, an exact equation, one of the, equations that we've learned how to do in our previous sections of Chapter 2. We have been here before in our earlier calculus journeys. Sometimes to solve a differential equation, we need to rewrite it using a change of variables. For example, we could rewrite dy dx equal to f at x and y using the substitution y is equal to some g of x and u, where u is a function of x. So if g has first partial derivatives, then applying the chain rule, we have dy dx equals, we have this g of x and u, right? Y equals g of x and u. So it would be the first partial of g with respect to x, and then just a little trick here, times dx over dx, plus that first partial of g with respect to u times du dx, because remember that u is a function of x. So this will give us dy dx equals the first partial of x at x and u, first partial of g at x and u, and plus the first partial at g with respect to u of x and u times du dx. So just rewriting it. Okay, and dy dx also equals f at x and y. Groovy? So substituting these things in for dy dx, we found the first partial of g with respect to x at x and u plus the first partial at g with respect to u at x and u times du dx. So all I did here is in for dy dx, I put all of this. Now on the other side of the equation, f at x and y is going to be f at x and g at x and u. So we're just substituting that one in for y, and that came from up here. Groovy? Okay, so now isolating du dx, let's see what we get. All right, so first partial of g with respect to u at x and u times du dx, and I think I might have said dy dx, we're isolating du dx, would equal to f at x and g at x and u minus the first partial of g with respect to x of x and u, just working on isolating du dx, cool, and then dividing both sides by the first partial of g with respect to u of that x and u to completely isolate du dx, we will get f at x and g at x and u minus the first partial of g with respect to x at x and u all over the first partial of g at x and u. Cool, cool? Now, what we do is we just rename this as du dx, so the other side will rename as capital F at x and u. Cool, cool? All right, so homogeneous equations, right? Homogeneous equations. If a function f has the property that f at tx and ty is equal to t raised to the alpha times f at x and y for some real number alpha, then f is said to be a homogeneous function of degree alpha. So let's just look at an example. Suppose we had something along the lines of f at x and y is equal to the square root of x plus the square root of y. If we evaluate f at t of x and t of y, we would get the square root of t at x plus the square root of t of y. This in turn would equal to, the square root function means that they're both raised to the 1/2, right? So we have t at x to the 1/2 plus quantity t at y to the 1/2. Factoring out a t to the 1/2, we would have root x plus root y remaining. And then continuing, what is that equal to? T to the 1/2 times f at x and y. Pretty cool, huh? So alpha in this case would be equal to 1/2. Sorry, I was ahead of myself. This would be t at 1/2 times this function of x and y. So we would have alpha is 1/2 in this case, and we would have a homogeneous function. Now, a first order differential equation in differential form. So remember, differential form had m at x and y dx plus n at x and y dy is said to be homogeneous if both coefficient functions m and n are homogeneous functions of the same degree. Or equivalently, m at tx and ty equals t to the alpha times m at x and y, and n at tx and ty is equal to t to the alpha times n at x and y, where alpha is the same. If m and n are homogeneous functions of degree alpha, we can make the substitution. So basically, this is the one that we typically use. If it doesn't work out, if it's too hard, then you can switch over to something else. But, and I don't want you to memorize any of these. If you have to memorize something, memorize, the substitution that you're going to do. So basically, you would start by saying, you know, y is equal to u times x. So then what would happen is you would get m of x and y equals x raised to some power times m at 1 and u. If you isolate u, please note, you would get u is equal to y over x. Okay? So basically, I'll write it a couple of ways. That is just factoring out some power of x, okay? And this in turn would equal to x to the alpha times m at 1 and u. Similarly, n at x and y would equal to x to the alpha times n at 1 comma y over x, which would be x to the alpha times n at 1 and u. Now, if that substitution didn't work, what you would do is you would try doing x equals v times y. So then isolating x, or isolating v, sorry, you would have x over y. So we would end up with m at x and y would equal to y to the alpha times m at x over y, comma 1. But x over y, of course, is v. So we'd have y to the alpha times m at v and 1. Cool, cool? And doing the same process for n, we would have y to the alpha times m at x over y, comma 1, which is y to the alpha times n at, this is an n, my bad, at v and 1. Groovy? So, these are the substitutions you would make. Again, I really don't want you to memorize these things, but when you continue to work it out, what ends up happening is this. So I'm going to work with the first version, this right here, okay? So what would happen is this. We would end up with m at 1 comma u, right? Dx plus n at 1 comma u times, so here we have the substitution, that first substitution, which was y is equal to u times x. So if that is the case, then the differentials would be dy is equal to u dx plus x du, and that is what you would substitute in for dy. So I will do so. And then all of that is equal to 0. Simplifying, we will have the following. M at 1 and u dx plus u, I'm just distributing this through, times n at 1 and u dx plus x times n at 1 and u du would equal to 0. Now, getting the dx's together, right, we're going to have m at 1 and u plus u times n at 1 and u. All of that times dx plus x times n at 1 and u du. All of that is equal to 0. So now, just to make things more easy to see, I'm going to separate these terms and get the dx terms on the left side, and on the right hand side we'll put the du term. So this is going to give us capital M at 1 and u plus u times n at 1 and u, this quantity, times dx equals to negative x times n at 1 and u du. Now I want to end up with dx over x. Okay, so when I do so, I will basically be dividing both sides. So first I'll isolate dx, just to make it clear, is negative x times capital N at 1 and u times du over m at 1 and u plus u times n at 1 and u. Cool? All right, so continuing, we will have dx over x, now I'm dividing through by x, is equal to negative n at 1 and u du over m at 1 and u plus u times n at 1 and u. So again, I really don't want you to memorize this. I want you to work through it each time, because otherwise it just won't make sense. This, I'm just showing you why. All right? Now, similarly, we can get, if you did the substitution, x is equal to v times y, you would have dx equals v dy plus y dv. And then working through it just like we did before, at the end of the day you would have dy over y, is equal to negative m at v and 1 dv over v times m at v and 1 plus n at v and 1. Okay? Now let's look at a couple examples. All right, example 1, please solve the given homogeneous differential equation by using an appropriate substitution. So we're told that this is homogeneous. All right? Now if you look, it's already written in the form where we can identify what m and n are. All right? And so let's see what we have going on. So I'm going to start by saying let y equal to u times x. And remember, we'll get dy is equal to u dx plus x times du using differentials. Okay? So now we have to put this substitution into our function, right? So everywhere I see a y, what do I put in? Beautiful, mu times x. Where I see dy, I put in this other equation. So let's do it. So we will have u times x, the quantity squared, plus u times x dx plus x squared times dy, which is u dx plus x du. So, in for y, I put u times x. In for dy, I put u dx plus x du. Cool? All right, let's keep going, trucking along. This is going to give us u squared times x squared plus u times x squared, all of that times dx, and then plus x, this is equal to 0, plus x squared, I'll put that u in there first, dx, u times x squared dx, and then plus x cubed du. So all I did is distribute the x squared to each term, and that's all equal to 0. Now remember, we want dx over x so we can solve this bad boy, right? So let's clean this stuff up. We'll have u squared times x squared dx plus u times x squared dx plus u times x squared dx equals negative x cubed du. That's the only du term, so I'm just getting it over there. All right? All right. So now what's going to happen here? Well, I can combine like terms, right? These two are like terms. So we'll have u squared times x squared dx plus 2 of these ux squared dx's is equal to negative x cubed du. Groovy? All right. Now we're going to factor out the terms that are with coefficient to the dx and also the x's. So the u's we're going to leave alone because we want to separate these variables. So we're going to factor out an x squared, and on the left side we'll be left with u squared plus 2u inside the parentheses, and then on the right side we'll factor out dx, and that's equal to our negative x cubed du. Cool? All right, and then now dividing both sides by x cubed, and then also basically separating the variables, I will get dx over x is equal to negative du over u, I'll factor, times u plus 2. Groovy? Now you might say, well, this still is kind of off, right? But that's okay because we have all of these neat tricks that we can do, right? So what I see set up right here is something that we want to run a partial fraction decomposition on, right? So let's come over here. When I do partial fraction decomposition on the right hand side, I'm going to have a over some u plus b over u plus 2. These are linear factors. I'm going to need a u term, so I'll have 0u, and then minus 1 is equal to that. Now I will go through and get a common denominator. This is all over u times u plus 2. When I get a common denominator, I'll have 0u minus 1 equals au plus 2a plus b times u. I don't need the denominator anymore. I'll equate the numerators. I will have quantity A plus B times U plus 2A to equate to the constant term. Equating coefficients, we get A plus B is 0 because they're both coefficients to U, and then 2 times A is negative 1. Well, here, actually, let's start with the bottom. A, we can solve to get negative 1/2 by dividing both sides by 2. And then that means that B must be positive 1/2. Groovy? So at the end of the day, we got negative 1 over U times U plus 2 equals negative 1/2 times 1 over U plus 1/2 times 1 over U plus 2. Writing it that way, getting ready to factor out the, constants. So when I write that over here, I will have this will equal to negative 1/2 times 1 over U plus positive 1/2 times 1 over U plus 2, all of that times du. And then on the left-hand side, I've got dx over x. Integrating both sides, now that we've got it all set up, what's going to happen? Well, we will have natural log at absolute x is equal to negative 1/2 natural log absolute u plus 1/2 natural log absolute u plus 2 plus some constant of integration. Groovy? All right, so now let's keep working with it. So bringing this over, I'll do kind of a dividing line over here. We will have I'm going to multiply everything by 2. So I want to clear the fractions out. So I will get natural log x squared. I no longer need the parentheses on it because it's squared, or not the parentheses, the absolute value bars. And then we will have on the right side natural log absolute. So there's a negative in front of the natural log absolute u, so that'll be in the denominator. So we will have u plus 2 over u in absolute value plus, call it some C1. And then getting all the natural logs together and bringing them together, we'll have natural log of absolute. The fraction will flip because we'll be subtracting the natural log on the right hand side. So it'll be x squared times u over u plus 2. Cool. And then that'll equal to our C1. Now let's substitute. What was u? U was equal to y was equal to ux. And so what does that mean? That means that if I isolate u, I will get y over x. So plugging that in for u, we will have natural log absolute x squared times y over x over y over x plus 2 equals C1. So all I did, wherever I saw a u, I placed a y over x. So then, simplifying through natural log absolute, we're going to get xy in the numerator. Getting a common denominator, we'll have y plus 2x all over x equals c1. And that will give us natural log absolute x squared y over y plus 2x equals c1. And we're all done. Isn't that cool? Groovy, groovy. All right. So now let's go ahead and take a look at this next one. We'll do one more example here. And this one will be, well, it'll need a little work, correct, to get this in the format we need, because we don't have our m and we don't have our n. So let's work on that first. So if I multiply both sides by dx, I'll get x times dy equals y times dx plus, I'll put this in rational exponents, x squared minus y squared to the 1/2 times dx. Cool, cool? Now let's get 0 on one side and then put those dx terms together. So we will have y plus x squared minus y squared to the 1/2, all of that times dx, and that'll all be negative because we got it over to the other side, plus x times dy equals 0. So again, let's go ahead and say that y is equal to u times x. Remember, we'll need the fact later that u is equal to y over x. And then let's check it out. Let's see, dy is equal to u dx plus x du. And then starting to work this bad boy out with our substitutions. We will have negative ux plus x squared minus ux, the quantity squared. All of that times dx plus x times dy equals 0. So in for y, I put u times x. And actually, we need to do something else, right? Before we say equals 0, we have to substitute in for dy. So dy is u times dx plus x times du, and all of that is 0. So dy is equal to this stuff. Then we crunch it all out and start doing our thing. So here we go. We'll have a negative. Then we will have u times x. And then I lost my 1/2 right here, my bad. Plus x squared minus u squared times x squared, all of that to the 1/2. And then this whole thing is times dx plus u times x dx plus x squared du equals 0. Okay, so I'll be able to factor an x squared out from that quantity in there. So let's work on that. I'm going to also distribute the negative. So we'll have negative u times x. When I distribute the dx, I'll get my dx. So I'm distributing the negative and the dx. And then we will have minus x squared. This is all inside this 1/2 business, okay? And then I'll have 1 minus u squared to the 1/2 dx. I'm going to get, and then we also have plus our u times x dx. And then I'm going to go ahead and get that du term on the other side to get a negative x squared du. Cool, cool? Okay, so now x is said to be greater than 0. So we're going to have, if you look at the two terms here, the u times x, we have a positive and a negative, so those are going to zero out, which is nice. And then we'll end up with negative x, I don't need absolute value because I know x is greater than 0, times 1 minus u squared to the 1/2 dx equals negative x squared du. The negatives go away, and when I divide by x squared, and then basically isolate dx over x, I will have du over, now maybe you'll recognize this better if I put it in terms of the square root when we go to integrate. We have this set up, so hopefully when you go to integrate, you'll recognize that we'll get the arc sine or inverse sine function, depending on how you like to write it. So we'll have natural log. I don't need the absolute value for the x because x is greater than 0. That's going to equal to, beautiful, arc sine at u over 1, which is u, plus our constant of integration. Isn't that cool? All right, so now I want to basically, okay, so let's isolate this arc sine function. So we're going to end up with arc sine at y over x is equal to natural log at x. If you subtract c, you get another constant. So I'm just going to say plus c1. And then evaluating the sine of both sides, we will have y over x is equal to sine at natural log at x plus some c1 and we're all done. Isn't that cool? I mean, you could isolate or y, so let's do that. That's not a hard one. X times sine at natural log at x plus c1, and we're all done. Awesome, awesome. Did I circle the answer last time? Yep. All right, perfect. Bernoulli's equation. So this is a fun one too. The differential equation, dy dx equals p at x times y. Whoops. The differential equation, dy dx plus p at x times y equals f at x. Now this one is something you're used to, right? This is that what we use the integrating factor for. But the difference is that you're going to have y raised to some power. Call it n, where n is any real number. This is called Bernoulli's equation. So for n equals 0 and n equals 1, this equation is linear, correct? But if n is not equal to 0 and not equal to 1, the substitution u is equal to y raised to the 1 minus n reduces any equation of this form to a linear equation. Pretty groovy, huh? All right, so let's check it out. In this second example, we have been given that this is a Bernoulli. So our substitution will be u is equal to y to the 1 minus n. Well, n is 2, so we'll have y to the 1 minus 2, which is y to the negative 1. So going with u equals y to the negative 1, y in turn is u to the negative 1. And finding the differential, we'll have dy equals negative u to the negative 2 times du. Cool, cool? So now, here we go. We're going to plug that stuff in. So we will have dy dx. So plugging negative u to the negative 2 du in for dy over dx minus y was equal to u to the negative 1. That's going to equal to e to the x times y squared, so you'll have u to the negative 1 squared. Cool, cool? So in for dy, we put in negative u to the negative 2 du, and in for y, we put u to the minus 1. All right, so now let's clear this up a bit. So now that we're done with our substitution, I'll go back to my favorite blue color. So here we go. Now the trick to this one is we want to write, we need to get our integrating factor, right? So let's isolate our du dx, all right? We'll isolate our du dx. And so I'm going to get rid of all these negative integrals, or negative exponents. So we're going to end up with negative 1 over u squared times du dx minus 1 over u equals e to the x times 1 over u squared. Groovy? All right. So now if I go ahead and multiply by u squared, do you see that we'll have just a function of x on the right, and then we will have, actually multiply by negative u squared, then we'll have a function of x on the right hand side, and on the left hand side we will have our du dx isolated. So here we go. Now this will give us du dx plus, I'm going to say 1 times u, so I can get my p of x, is equal to negative e to the x. Now this one is in linear form. So coming back over here, my p of x is positive 1. My f of x is negative e to the negative e to the positive x. My integrating factor will be e to the integral of 1 dx, which is just e to the x. Cool, cool? And now, multiplying both sides by my integrating factor, I will have e to the x times du dx plus e to the x times u equals negative e to the 2x. Now remember, the left-hand side is a derivative with respect to x. So if you rewrite the left-hand side as d dx of e to the x times u, do you see that the line above is its derivative? And so we'll have negative e to the 2x on the right side. Now, multiplying both sides by dx, we'll have e to the x du is equal to negative e to the 2x dx. Well, in order to integrate, I need a factor of 2, so I'll set that up here. And then integrating both sides, we will have a result of e to the x times u is equal to negative 1/2 e to the 2x plus some constant. Now, what was u? U was y to the negative 1. So we'll have e to the x times 1 over y is equal to negative 1/2 e to the 2x plus c. Now getting the exponential terms together on one side. Actually, yeah, we'll get the exponentials. We'll isolate the 1 over y by multiplying both sides by e to the negative x. So the first term will have negative 1/2 e to the x, and then we'll have plus e, sorry, we have a c, e to the negative x. And we're all done. Groovy? All right, beautiful. Now, last one for the day. Sometimes you're going to do a different type of substitution, okay? So here, with something like this, we've got a substitution that we kind of play around with. This is where you have it in the form of, say, ax plus bx plus c. So what we're going to do here is we're going to let u equal to 3x plus 2y. So differentiating with respect to x, we'll get du dx will be 3, that one's explicit, plus 2 dy dx. Cool, cool? So just a little more work here. We've got what du dx equals, okay? We're going to kind of keep that to the side. Now, if we start looking at what is dy dx, because that's what we have on the left-hand side of our equation, we would have 2 times dy dx is equal to what? Good. Du dx minus 3. So isolating dy dx, we would have 1/2 du dx minus 3/2. On the left-hand side, we would have 1/2 du dx minus 3/2 equals, making our substitutions, u was equal to 3x plus 2y, and then we would have u plus 2. So u was 3x plus 2y from over here, and then our du, or dy dx rather, was all of this stuff, which is on the left. Groovy? All right, now we've got things in terms of du dx, so simplifying, let's see what we have. So, factoring out a 1/2, we would have du dx minus 1 is equal to u over u plus 2. Multiplying both sides by 2, we'll have du dx minus 1 equals 2u over u plus 2. And so du dx, and I apologize, this is 3 minus 3, not 1. Du dx would be positive 3 plus 2u over u plus 2. Cool, cool? All right, so now let's go ahead and see what we would have to do here, all right, to solve. When I'm, going through, I need to get, let's try getting a common denominator, all right? So 3 times u plus 2 plus 2u all over u plus 2, just multiplying 3 by u over 2 plus u over 2, we get du dx is equal to 3u plus 2u is 5u plus 6 over u plus 2. Cool so far? Now, let's go ahead and separate the variables. So now we'll get u plus 2 over 5u plus 6 times du is equal to dx. So notice that we have the same degree, so we can do long division, polynomial long division. So quantity 5u plus 6 goes into u plus 2. Be careful, you want to match that coefficient so of the u, so 1/5 is what we multiply through. So we would end up having u and then plus 6/5. We're subtracting that, and then we will get, what is that, 10/5 minus 6/5 is 4/5. So this would be plus 4/5 over 5u plus 6. Groovy? All right. So now we're going to rewrite it in that term. So this would be 1/5. We can factor out that 4/5 times 1 over 5u plus 6 du equals dx. Now, in order to integrate that last one, we are going to need a factor of 5, aren't we? So if we multiply by, because of the 5u plus 6 denominator, so I'm going to multiply by 1/5, and then integrating both sides, we will have 1/5 u plus 4/25 natural log absolute 5u plus 6 equals x plus c. Now I am going to back substitute. So we'll have 1/5 times, remember u was 3x plus 2y, plus 4/25 natural log absolute 5 times 3x plus 2y plus another 6 equals x plus c. And so I just back substituted what our u was into these results. So then, cleaning it up a bit, we would have 1/5 times 3x plus 2y plus 4/25 times natural log absolute 15x plus 10y plus 6 equals x plus c. Now, using our initial condition, what was that? Y at -1 is -1. We will have 1/5 times 3 times negative 1 plus 2 times negative 1 plus 4/25. Sorry, there's an end parenthesis. And then plus 4/25 times natural log absolute 15 times negative 1 plus 10 times negative 1 plus 6 equals negative 1 plus c. So in for y, we put negative 1, and in for x, we put negative 1. So I think we're all substituted. So then we will have negative 3 plus negative 2 is negative 5. Over 5 is negative 1. Plus 4/25 natural log, we would end up getting negative 15 minus 10 is negative 25 plus 6, I believe is negative 19, but the absolute value of that is positive 19, equals negative 1 plus c. The negative 1 zero out, and so c equals 4/25 natural log 19. So plugging it all back in, all right, we would have 1/5 times 3x, sorry, I forgot a parenthesis there, 3x plus 2y plus 4/25 times natural log absolute 15x plus 10y plus 6 equals x plus 4/25 natural log 19. Groovy? And that's it. That's good. All right, beautiful. Well, I hope you have a wonderful morning, afternoon, or evening whenever you're watching this show. And if you like what I'm doing, hit that like button and please subscribe. Bye.